And next speaker will be Leonid Berlyand from Penn State University, which will talk about homogenized description of vortex phase separation in superconductors with holes.
Well, so this is the title, and I've been working in Ginzburg-Landau vortices for about, I would say, 15 years since I read this wonderful paper by Brzezinski, Berlyand, and Helene. And all of my work in this area was motivated primarily by mathematical challenge and mathematical beauty. Now, this work is somewhat different. So in this work, we actually were trying to address some physical issue which was brought to my attention by my colleague, physicist from Argonne, Valery Vinokour, and we ended up writing one mathematical paper and one physics paper jointly with him. So the purpose here is not to just flex my mathematical muscles and impress you by beauty, but rather show you how we can address, using available mathematical tools, this fundamental issue in superconductors, physical issue. And the talk will have kind of two levels. One is general idea, what's going on, but because it's a school and because Liao already presented a number of detailed calculations and introductions to vortices, I would also put some technical details for the sake of students who are here to learn. Okay, so basically here is the outline. I'll start from brief review on work on pinning. Then I do the physical problem, and then I'll do mathematical analysis of it and conclusions. So first of all, let me remind you the issue of pinning, which my colleague Valery Vinokour already presented. You've heard a lot about vortices. And from practical standpoint, what happens in superconductor, vortices do move. And when they move, they dissipate energy, and this is bad, practically. So pinning, namely fixing location of vortices, preventing them from moving, immobilizing vortices, it's therefore an important practical issue. And one has to understand how it works. So for this particular problem, which I will be talking today, our question was how special choice of parameters, special scaling of physics and geometry in the problem can lead to unusual vortex pattern of pinned vortices, something which was not observed before. Okay, what you can do by playing as a control parameters sizes of holes in composite materials versus strength of magnetic field, roughly speaking. Now, mathematical models of pinning with finitely many size. That goes back to Lasso, Mironescu, and then Alama Bronsard, Dos Santos Misets, more recently Kachmer. But this is finitely many sides. So this work adds one more layer of difficulty, namely when there are infinitely many, large number, physically and mathematically asymptotics, homogenization. Okay? As to homogenization, not much have been done. There is old work, relatively old, by Aftaleon, Sandier, Serfati. This is not with holes. This is rapidly oscillating continuous spinning term. And for our model of composite with hole, this technique would not apply. But this is where first both pinning and homogenization was considered. And more recently, my former students, Alex Misets, with collaborators, Dos Santos and Mironescu, considered simplified Ginzburg-Landau, which you already have heard what it is, when there is no magnetic field. And they obtain homogenized solution with no vortices. So in terms of vortex pattern, it didn't answer any questions, but it's a playground to develop some techniques which would combine pinning and homogenization, infinitely many pinning sites. So this is the motivating physical problem. it's a superconductor with columnar defects, which are straight columns of damaged materials. And you can obtain them by high energy irradiation. And these defects, they naturally pin these vortices. They immobilize vortices. And that produces certain pattern. And if magnetic field is aligned with columns, with columnar defects, then the pinning becomes quite efficient, and mathematically it reduces to a two-dimensional problem, which is easier to analyze. So I mentioned that homogenization was mostly done of non-smooth coefficients like defects for simplified Ginzburg-Landau. But let me also remark here that while simplified Ginzburg-Landau, that is with no magnetic field, works well when there are finitely many vortices, when there are infinitely many vortices, it was shown by Sandier and Soret that instead of Abrikosov lattice, which is a signature of superconductivity, vortices concentrate near boundary. So in other words, you can develop some mathematical tools, but if you want to describe some physical phenomenon, one has to consider functional with magnetic field. And one thing, what we were expecting, let's compare what our problem with a well-known case of magnetic field and homogeneous superconductor, no holes. Then effective homogenized vorticity is large number of simple vortices, and what we are after, what would be main result of this work, that by contrast in this problem, which is A, we have pinning sites, so it's not inhomogeneous superconductor, and B, we have special choice of scaling parameters, physical and geometrical parameter. We shall obtain a new pattern which was not observed before, namely multiple vortices in nested subdomain with sharp boundaries. And I will explain later. This is kind of abstract style telling you what to expect. And also, you already heard definition of vortex, which is zero of order parameter with non-zero degree. Here we are talking about, I call vortex something which is whole vortex, namely it's not zero of order parameters, but it's a vortex in a hole when degree around hole is an integer. Okay, so that's what the word vortex would mean throughout this talk. And this represents this columnar defect, for example. So what is the issue? What is the physical issue? So in most of physical typical experiments from the first observation of Abrikosov lattice, the pattern of vortices is uniform throughout superconductor. And one of these is a classical Abrikosov lattice. However, and there are hundreds of papers in different kind of angles of this. Now, there is few papers, for example, this one, which was brought to my attention by Valery Vinokour, when it was somewhat unusual experimental observations. Multi-quanta vortices were observed, but there was no theoretical underpinning, or maybe it's something not quite right with experimental mistakes. So what we want to understand this phenomenon and formulate it as a vortex phase separation, and then try to see how it can be useful. And here, one of the main things was to choose holes which are very, very tiny. And with modern technology, I was told that if we predict something which is useful, it's possible to do it now in lab. Okay, so the scaling is not artificial. So now what I should do, again, it's brief overview. I shall start from harmonic map type model, namely when potential term is replaced by this constraint. So it's sort of like harmonic map for simplified Ginzburg-Landau. And next, I will relate this simplified problem to original problem, full problem, this nonlinear term. So this is the formulation of problem. Now I'm formulating you a model, mathematical model. And then I will analyze it. So we consider, as I said, the columnar defects are aligned with axis of cylinder and with magnetic field. So effectively, problem is two-dimensional. So those are holes of size rho. Distance between them is epsilon. This is homogenization parameter. And this is a scaling relation. Ginzburg-Landau parameter, inverse to Ginzburg-Landau parameter is small. This is something which you learn already is related to coherence length. This is the smallest parameter in the system when Cooper pairs start to talk to each other. It's much smaller than radius of the hole, but this is much smaller than distance between holes. So in homogenization, this geometry is called dilute regime. And we need to consider this functional in a perforated domain, omega epsilon. And we want to find homogenized or limiting vorticity measure of this minimizer is u epsilon a epsilon when vortices are pinned by holes. So again, let me bring analogy. So let's consider homogeneous superconductor, very well-known case. Then if applied magnetic field is less than first critical field, then there is no vortices in the bulk. And vortices, if exist, they are pinned by holes. Then we increase magnetic field, and then vortices started emerging in the bulk. For domains with holes, we need to break this first interval when there is no bulk vortices. Bulk means outside, that's in homogeneous superconductor, into two. No vortices at all, and then vortices inside holes, but not in the bulk. And then you can go further. So as I said, scaling plays here crucial role. And we assume here we consider the case when magnetic field, integral of magnetic field per cell, and cells is of size epsilon, so its area epsilon square is finite. And that means that magnetic field is weak like this, epsilon minus 2. And this constant will actually will help us to tune multiplicity of vortices later. Now, since effective core of the vortex is now radius of the hole, then simple energy consideration shows then the radius of the hole should be exponentially small for this to make sense. So it's a much stronger separation than just rho less than epsilon. So it's exponentially small. And this is what you will see, that this choice of scaling is absolutely critical. So thus we introduce this strong scale separation in the following. This is Ginzburg-Landau, inverse Ginzburg-Landau parameter, which is material parameter in my functional. This is radius of the hole, logarithm, and this is epsilon is distance between holes. And we consider magnetic field of this order, which is less than first critical, and therefore there is no vortices in the bulk. Now, the problem which I'm going to start with and rigorously analyze and prove something about is the following reduced version of previous functional. Namely, u is here. We minimize this functional. Notice there is no potential term. Why? Because we consider u in class of S1 valued function. Okay? And so my problem would be to find minimizer of this variational problem, determine degrees, and see how and find non-uniform pattern, which I'm after. So then what I'm going to show you later that, and this is my student, Alex Yaroshenko, will be speaking. I'm going to just mention this, that actually in terms of this reduced problem, in terms of vorticity, is equivalent to the original problem, which is a big advance because this is much simpler to analyze numerically and in many other ways. Okay? So while, of course, minimizers are not the same, the degrees, the vorticity pattern is the same. And that's an interesting issue by itself. But for now, I'll concentrate on analysis of variational problem for this reduced functional. So let me explain you what do I mean by vorticity, because I want to do something rigorously mathematically. So if I have a function with degrees di epsilon, and then I can define vorticity measure like that, and I can define its weak limit if my di epsilon are bounded. And what my goal would be to establish homogenization result, to find this homogenization result in terms of vorticity, not in usual sense. I don't care now about U, about order parameter or magnetic field. The observable thing is this vorticity pattern. So that's this. I would like to obtain certain variational problem whose minimizer will define the limit vorticity measure. And that's, again, in a kind of abstract style, this is how it will look like. It's going to be a certain minimization problem, and phi star would be obtained for, which is nonlinear term, which would obtain from gamma limit. This is homogenized problem. This is omega. There is no holes. This is homogenized problem already. Holes were here when was epsilon. It's like an usual problem for Laplace. When you have holes of size epsilon, when you take the limit integration over omega, there is no epsilon, there is no holes. Okay, they are effectively replaced by this vorticity. Okay, good question. Yeah. All right. So how minimization problem works here? So we minimize the harmonic type energy in two steps, which results in a coupled discrete continuum problem with quantization constraint. That's from mathematical point of view, it's a main obstacle for using straightforward classical homogenization. So first, in general, my di's are not known. My di's are degrees of my vortices, or winding numbers of my vortices. They're not known. But let me first consider problem for magnetic field. Those are early Lagrange equations for my variational problem. But the only glitch here is that di considered given. So if I solve this problem, I find my magnetic field, which is curl A, as a function of di's. Then I plug this into my energy, which depends on h epsilon, and I obtain this as a functional, not of a function, but on tuple of integers, which is expanding. So it's not standard gamma convergence, because we go where physics takes us. So it's gamma convergence. I have to study this functional as a function of integer tuples whose size of this tuple goes to infinity, and in the limit, gamma limit should be a continuum problem. Okay, this is the setting. It's an interesting setting for gamma limit. So basically, I have to minimize this thing with respect to all these integers, and that gives me my vorticity pattern. And homogenization objective would be first to obtain limiting h epsilon. What's a homogenization limit of this problem when epsilon goes to 0? So let me also mention some references here, because this coupled discrete problem, we didn't invent it. It was first formulated for finite number of holes in paper by Sten Alama and Leah Bronsart. In this case, though, because there are finitely many holes, what happens when magnetic field grows, the degrees of vorticity in each hole goes to infinity. Okay? There is no then effect of integer constraints, because million or integer part of billion is the same. Okay? So here, because of infinitely many pinning sites and fine scaling, it's fine-tuned so that it's enough pin-in sites to have finite degree of vortex in each pin-in site. Okay? That's why one can have this beautiful vorticity pattern. So we have large number of holes. This is a number of holes, which is lattice number of points in a mesh of epsilon size. And this is the size of magnetic field, and they're fine-tuned. So we expect to have holes or vortices of finite multiplicity, but not simple multiplicity as in homogeneous superconductor. And then we have to precisely formulate these conditions, and that's what our analysis should tell us. So let me do homogenization first on a PDE level, and then translate it into vorticity. So first, as usually in homogenization, there is a weak convergence in H1 of H epsilon to H bar. Now, I don't consider H epsilon, but rather H epsilon square. Why? Because external magnetic field is of order of H minus 2, so therefore I have to scale to obtain something finite. Okay? So this is explanation of scaling. Now, if I do this, that would be application of standard homogenization techniques. Then I'll obtain this equation. And then I obtained my vorticity as a weak limit. However, if I need to consider convergence of energies, I need convergence of derivatives. This is a well-known problem in classical homogenization. When you start first result of homogenization for Laplacian or divergence form equation were weak convergence, which doesn't tell you much practically because stresses, currents, they're all derivatives. So then the next step in homogenization was introduction of corrector, something which converts weak convergence into strong convergence. And here we have to do it in this unusual setting because now we have functional integers. It's not classical setting at all for gamma convergence. So first, then let me consider my functional, which is actually functional on integer tuples, as I explained before. I have to scale it properly according to epsilon square. Now it's epsilon to the 4. And if I'm after gamma convergence, I have to establish lim inf and lim sup condition. And of course, lim inf is usually difficult, as usually in gamma convergence. And this is because we need convergence of energies and to get optimal lower bound. So how gamma convergence should work, we have to have upper bound, lower bound, and they have to match. So, this classical techniques would not be sufficient, and we have to do something more. And we will, and I explain how, but let me just say that this is what's going to come up at the end. The energy, limited energy in terms of limited H, plus some function, which I will explain where it appears, this of D. Now, this functional is functional of vorticity, even though here is H bar. Why? Because H bar is related. So eventually it has to be considered as a function of vorticity, because my objective is not to study magnetic field or order parameter, but to see vorticity picture. Okay? And phi would be some piecewise linear approximation for quadratic functions at the end. So this is kind of announcement of result in a broad terms, not very detailed, but I will formulate very detailed theorem. So how to find gamma limit? I already explained you that this is not sufficient. This converges to this only weakly, so I need this corrector. And this is usually the hardest problem. It's the heart of mathematical homogenization. It's still in periodic homogenization. It's well understood. You go to random ergodic system. Limits are very well known. Corrector only one-dimensional. It's a big issue. Okay, so construction of corrector is an art in each particular problem, unless standard techniques applies. So here we also fought quite a bit, and we constructed corrector in this form, but this comes from my previous work on Dirichlet boundary conditions for elliptic problems. And I won't go into details of this, but that's basically how solution looks like. This is homogenized, and this is what corrector does. So it's exponentially thin peaks. They add it to smooth solution. And it's truncated on the whole. It's only positive part of it. So then in order to find gamma limit, which is the key mathematical tool here, we need to consider energy of this minimizer and then represent it as leading term plus corrector. You open this up, cross terms disappeared, and the main thing would be to calculate this term which is due to corrector, which is energy, contribution of energy due to corrector. Now notice what is the difficulty here. What we have convergence of this measure, vorticity measure, remember, to limiting distribution. Now here there are first powers of D. And the convergence is weak. But we all very well know that weak convergence of functions does not imply weak convergence of squared of function with sine x over epsilon is a classical example. So we have to do something about that. But also note that there is some specific observation here. If vortices happen to be simple, no multiplicity, then all di's are 1s or 0. Then there is no issue between here and here. Square, not square, doesn't matter. But because in this physical system vortices can be multiple, that's become an issue. So we only have convergence of this. How to get this? And here there is one more tool we introduce in this paper, something which is called spread measure, which basically analog of Young measures on a discrete set of integers. So we redefine my d epsilon as k mu k of epsilon, where mu k is equal 1 if in this cell pi, this is pi epsilon j's periodicity cell, vorticity happen to be equal to k, and if not, it's 0. So basically, it's like counting functions, so it's like expectation, okay, or first moment. So then this mu k epsilon, they form a partition of unity with standard properties of partition of unity. Sum is 1, positive, non-intersecting support. Then one can check that this family is L2 bounded, and one can check tightness. This is a technical issue because one has to prove boundness of these degrees, a priori bounds, but we've done all this. And then from tightness, you obtain existence of limit, as usually in measure theory. And then we show that d of x is actually limit. In the limit is mu bar k of x. And we try, but for lower bound, we have to deal, remember, with squares. So we need something which would be of this type. And then we need to minimize second moment over all partitions mu k to get true lower bound. And to illustrate this issue, let me just give you a simple example. So let's take two cells, and let's take vorticity -1 and 1, degree -1. So that's mu1 would be 1/2, mu -1 would be 1/2, and first moment would be 0. D would be 0. Now I take 0, 0. First moment is the same, but second moment can be completely different, and I need to compute second moment. So what I'm saying that, again, more work here is needed, and that's what's done in framework of this Young measures. So finally, here we obtain that lim inf is bounded by leading term plus second moment, and we have to minimize this second moment in mu k, subject to given constraints, that it's partition of unity and fixed first moment. So then this minimization with constraints lead us to this function phi of d, which I promised you at the first slide, which happened to be like piecewise linear approximation of parabola. It's not surprising. The parabola because of d squared, because of squared, but because of quantization, we always have to, the practical obstacle in applying straightforward tool is quantization, which is unusual. Okay, and that's what actually spirit of this workshop was, to relate classical and quantized vortices. But that's a calculation which eventually gives us phi of d, and then we know that d, this is the theorem, let d epsilon be integers degrees of minimizer u epsilon, and under the scaling which I described you, exponentially small holes and external field epsilon minus 2, we have this convergence where d minimizes functional with phi, which we just defined, and h is defined via boundary value problem. So this is homogenization result, but it's not my final product. When you do homogenization theory, you stop right there, but I want to observe, I want to study this d. And namely, I want to study how d depends on this sigma, how it looks like. And that would be my next analysis.
Can you say what's the contribution of the corrector term?
Yeah, contribution of corrector term is here. Yes, this is non-trivial part. Yes, exactly. Here, they actually corrector and leading terms are of the same order, contribution, but in two different. And this is non-trivial part, non-local part is due to corrector. It's a very good question. What?
You're not restricted to 1D?
No. It's a two-dimensional, yes. No, in 1D, I mentioned 1D, not to confuse you. When I mention an issue of corrector, which is well studied in periodic homogenization, this issue, the same issue in random homogenization, is wide open except one dimensions. Okay, but here there is no randomness yet, but you will see randomness at the end. I mean, first I want to do periodic, and then I'll announce something which is in progress about randomness. So far, yes, 1D needed when we go to randomness. So let me recall that homogenization problem looks like this for effective vorticity, and we can formulate it. Let me just try to simplify it, because I want to analyze it. I want to lay my hands on D and say something qualitatively, how D looks like. What is a picture of D? So first let me get rid of inhomogeneous boundary conditions. Then this is how my problem would be written. Minimization subject to these constraints, H1, and also Laplacian has to be in L2. This is because of this term. So there is a known trick which goes back to Serfati and Brizis, that in problems of this type, it's much easier to analyze if you go to Legendre dual problem. Notice this is a calculation, but what it shows that here there is no this constraint. So what we would like to do, we would like to analyze, and minimizers are the same. Okay, so we would like to analyze something which is simpler. And let me just briefly mention again, I'm now entering some technicalities, so here I will not be very detailed, but just telling you that it's a calculation to compute phi star from phi, psi star from phi star using the Legendre transform, but eventually that's how this function looks like. So now, remember my vorticity was function of f, and in order to find f, I need to minimize this dual problem where phi star is also computed. And there is a formula which relates my vorticity with f, which I showed you before. If you don't remember, that's fine. But at this point, what's important, if I found f, minimizer of this problem, I found d. And then I can analyze it. So here is the main result, main mathematical result, which shows the following. Suppose I'm under my tricky scaling, exponentially small holes, and weak magnetic field. It's weak because there is no bulk vortices. I am still in periodic setting. Then I can start increasing this sigma, which does not depend on epsilon. And there are sequence of values which depends only on gamma, and gamma is here, and omega, such that if sigma is between two critical values, then limiting vorticity takes constant values. So basically, let me explain you. So you start from we start from lowest sigma, and then vorticity is equal 0 here. Then you start increasing, and then you start noticing appearance of nested subdomain with d of x is equal 1, d of x is equal 2, and the very last one, it doesn't have to be integer. Non-integer means vorticity means that they're mixed, for example, 0 and 1, so vorticity would be 1/2. Okay, not all sides. That's what non-integer vorticity, which can puzzle you. So that's a pretty picture, which Valeria already showed you, but that's what we discovered back with Rybalka, and then we were able to interpret it, and Valeria actually added a lot. He also established some soliton structure, which I'm not going to talk about, which he explained in his lecture yesterday of electric field, so it's very new and very interesting soliton type of structure of electric field, but I will concentrate in this talk on vorticity only. Okay, how much time do I have? What? 25 minutes. Okay, then let me just go. Okay, so let me just illustrate it how this domain arises. So we consider first sigma between 0 and some value sigma 1, which depends on gamma and some boundary value problem, and I can tell you where it comes from. Then this is a graph of function phi star, and then one can show that in this case d of x is equal 0. So there is no vortices at all. And once you moved, next, what happens, what happens is that already I moved 2 steps up. I actually skipped 1 step. Let me see if no, it's skipped. So here it's already 3 subdomains, 0, 1, and something between 1 and 2. And just to give you a spirit, not to explain maybe, the variational problem for f becomes obstacle type of problem because of this structure of function phi star. I know it's probably hard to follow if you never saw it, but obstacle problem in Ginzburg-Landau are very well known, so it's not surprising that this appears here. This is not a big discovery. The discovery was this multiplicity, which never appeared before. And the other thing which I would like to point out is sharp boundaries between domains. So most of known distributions of vortices, not most, everything which we know were smooth. Okay, here we are predicting that for this special choice of scaling, you can have sharp boundaries. So the natural question to ask would be, what if not that special scaling? What would happen? And it's not completely answered rigorously, but intuitively, if you consider larger holes, essentially larger, not with a constant, then one can arrive with uniform vorticity, but again, it's a question mark. It's an ongoing project of Sasha Yaroshenko, who will speak on Thursday. Now, very small holes, it's not difficult to establish. They're just like no holes. Okay, so there is no effect. So basically, if scaling is different, then this terrace vortex structure is expected, and the natural question is how robust is this terraced vortex structure, which is also current work. How much you can change scaling, sizes, and magnetic field so that you still have this terrace structure present. Okay. So let me say a few words. Remember what I did first. I started from, let me go back and then remind you what the issue was at the very beginning. I have time, I think. So Okay. I started from Ginzburg-Landau through Ginzburg-Landau functional with nonlinear potential term and formulated problem of vorticity here. And then I kind of cheated and started to solve, actually. All my theorem were proved for this function, which is much simpler, okay, because there is no potential term. And the question is whether in terms of vorticity they're equivalent. Obviously, minimizers are different, but this one accurately captured vorticity. And that is Sasha's work. And with us, so let me just show you. So first, natural setting to investigate, what we ask him to do is, in a setting of one hole, but also exponentially small hole, prove that minimization of full problem and minimization of reduced problem leads to the same vorticity. Why this setting? Because, of course, you understand it's separable setting, symmetric setting. You can use Bessel functions. You can lay your hands on the solution. And in a nutshell, you will hear all details on Thursday, but basically we use energy decomposition in terms of harmonic map energy and plus remainder. And then we show that except one special case of sigma, the minimizer of truncated problem or reduced problem and minimizer of full Ginzburg-Landau problem with nonlinear term, they have exact same degree. And this is intriguing where this constant comes from. So sigma has to satisfy certain condition for this to happen, and that's what he will explain on Thursday. This is Bessel function. So roughly speaking, degree is integer part of this, and if it happens to be exactly between two integers, then minimizer would not know what to choose. Okay, that's why we have to explain. All right. Now, very interesting recent developments with my other graduate student, Sean Ryan, who is not here. Two of them are here. And this is the following question. What if randomness comes into play? What if we replace? It's a very natural question. And we know how fundamental this question is. Sometimes, like standard divergence form homogenization of periodic and random ergodic problems gives you more or less the same result. Laplacian in the limit, same form of operator, except cell problem is now not on a cell, but on an infinite plane. So, in other words, if you replace periodicity by statistical periodicity, which is stationary ergodic random field, nothing essentially changes. It becomes just harder technically. On the other hand, we know examples like Anderson localization, when you replace Hill's equation with very well-known structure of spectrum, you replace by random, and life is completely different. It's localization. So that's why, changing this passage from periodic to random is not at all trivial, and it can bring surprises. And that's what we are after. So in this, I just very briefly tell you. So what do I have? 10 minutes? Okay. So this ongoing work, which is not finished yet, the point is to develop analytical methods for arbitrary hole locations based on functional equations. So we have certain given realization, and we try to analytically to predict, to solve it to some extent, and then use numerics to obtain final picture. So it's not direct simulations, not at all. So it's a serious analysis just in spirit of homogenization. What do? You first obtain analytically a problem, and then you solve a cell problem in order to find final number, which is much simpler than original problem, which does not depend on small parameter. Something like that here. So basically, the idea is to replace periodic geometry by random Poisson distribution with non-overlapping conditions. And roughly speaking, what kind of results we are getting, and again, this is work in progress, is the following. That these sharp boundaries, those are numerical illustration. The sharp boundaries becomes not much less sharp. So the subdomains now, the interfaces have Hausdorff dimension 1.3. Critical magnetic field for formation of whole vortices decreases essentially. And distance of those interfaces, they become much closer to the boundary. So this nested terrace structure becomes very significantly modified, but it's still there. Okay? And with that, let me come to conclusions. So let me just summarize what you have seen today. So we started from the issue that in most of experiments observed either uniform vortex pattern or very few observed something where it was not quite uniform, but it was also smooth, always smooth. Can we predict something which would be departure from this picture? And I'm not talking now why it would be helpful. It's just a fundamental physical question. Okay? And and what we did, we found appropriate scaling, namely relation between physics parameters, which are here magnetic, applied magnetic field, and geometric parameters, geometry of holes, such that we observe vortex phase separation. And this marks a serious departure from current understanding of ground state in macroscopic system. In fact, a random system, there is not much even known about this ground state. So this second work, hopefully, if it all works out, would be even more interesting. Now, it did require introducing of some interesting and novel mathematical issues and challenges. And first was reduction of full to harmonic map problem or equivalence of vorticities. And second was this unusual setting for gamma convergence. Classical gamma convergence is convergence of energies, right? Energy functionals. Here, the functional is function of integer tuples of increasing length. And in the limit, you obtain continuum. And this quantization is always technically on the way. You have to deal something because all classical gamma convergence is not for quantized quantities. Okay? And for that, we developed relevant analog of Young measures and specific gamma convergence techniques. And finally, this randomness is very promising. For now, we have mixture of analytical and numerical results. And hopefully next time I will be able to report on that. And with that, let me stop. And thank you for your attention.